Hey everyone. When you're designing algorithms, you start to see the same patterns pop up again and again. Well, today, we're going to tackle one of the big ones, a real classic recurrence relation that you will definitely see. T of n equals T of n over 2 plus n. Let's really break this thing down.
So here's the million-dollar question for every programmer, right? How do you know if the code you're about to write is going to be super fast or if it's just going to crawl to a halt? I mean, before you spend all that time actually building it. Well, the secret sauce is understanding these things called recurrence relations. Think of them as the mathematical blueprint for how your algorithm's going to perform.
All right, so here's our game plan. First, we'll decode what this equation is even saying. Then we're going to hit it with two powerful methods. First, the visual recursion tree, and then the more algebraic substitution method. And finally, we'll wrap it all up with the key takeaways you need to know.
Okay, first things first. Let's just figure out what we're looking at. This isn't just some random math equation. It's actually telling a story about how a specific kind of algorithm works.
At its heart, a recurrence relation is basically the language of divide and conquer algorithms. It's a formula that says, hey, the cost of solving this big problem of size n, well, it depends on the cost of solving smaller pieces of itself, plus whatever work you have to do to split it up and put it back together.
So let's apply that to our equation. T of n, that's our total time, our total cost. The T of n over 2 part, that's the recursive call. That's the cost of solving a problem that's exactly half the size of the original. And that plus n hanging on the end, that's the work we do at each step to divide the problem and then combine the results later.
All right, let's get visual. Our first method for solving this is the recursion tree. Honestly, this is such a great way to build an intuition for what's happening, because you can literally see the work being done at each step of the recursion.
So we always start at the top, at the root of the tree. This is our first function call, with the full problem of size n. And according to our formula, the work done at this level is simply n. Easy enough.
Now we go one level deeper. Our main problem, T of n, makes a single recursive call on a problem half the size, right? T of n over 2. So what's the cost at this new level? Well, following the formula, the cost is proportional to its input size, so it's n over 2. And you can probably guess what happens next. That T of n over 2 problem calls a T of n over 4 problem. The cost for this step? You got it, it's n over 4. We've got a really clear pattern emerging here. Every time we go down a level in the tree, the cost for that level gets cut in half. And this just keeps on going, level after level. The cost is n, then n over 2, then n over 4, and so on, until the problem gets so tiny, down to a size of 1, that it's trivial to solve. That's what we call our base case.
Okay, so we've built out this beautiful tree. Now what? Well, now we have to figure out the total amount of work being done. And to do that, we just have to add up the cost of every single level.
This table really lays it all out for us. Level 0 is n. Level 1 is n over 2. Level 2, n over 4. You see the pattern. What we're staring at is a classic geometric series. So to get the total work, we sum up all those costs. N plus n over 2 plus n over 4 and on and on. Now, a little math trick here. We can factor out that n. And when we do that, we get n times the series 1 plus a half plus a quarter plus an eighth. The entire problem now boils down to figuring out what that series in the parentheses adds up to.
So think about it like this. Imagine I give you a pizza, and you take half of it. Then you take half of what's left. That's a quarter. And half of that, which is an eighth. If you keep adding up those smaller and smaller pieces, you'll get closer and closer to having a whole second pizza, but you'll never quite get there. That series, 1 plus a half plus a quarter and so on, it actually converges to a very specific number. It converges to 2.
And this chart really drives home the main point. The work we do at the very first step, at the root of the tree, that single n, is basically half of all the work we're ever going to do. It's equal to the sum of all the other levels combined. This is why we say the work for this algorithm is front-loaded. The initial call does the bulk of the work.
So what's our final answer? The total work is n, multiplied by that series, which we now know converges to 2. So the work is roughly 2n. But when we talk about big O notation, we don't really care about constant factors like 2. We're interested in the growth rate. So we drop the constant, and the complexity is simply big O of n.
Okay, now for method number 2, substitution. If you're not a fan of drawing trees and you just prefer to stick with the algebra, this one's for you. But what's cool is that it's going to tell us the exact same story.
We start with our original equation. Now, we know what T of n over 2 is, right? Based on the same formula. It's just T of n over 4 plus n over 2. So, we're just going to substitute that expression back into our original equation. All we're doing is unwrapping the recursion, one step at a time.
Let's just do it one more time so the pattern becomes crystal clear. We take that t of n over 4 term and substitute its definition in. And what do we get? We get t of n is equal to t of n over 8 plus n over 4 plus n over 2 plus n. Hey, that looks familiar. It's the exact same geometric series we saw with the tree method, just written out horizontally.
And there you have it, side by side. The recursion tree built the sum vertically, one level at a time. The substitution method built the exact same sum horizontally, one expansion at a time. They're just two different ways of looking at the same problem. And, no surprise, they both lead to the same exact conclusion. The complexity is O of n.
So, let's wrap this up. What is the absolute bottom line here? If you're studying for an exam or prepping for a technical interview, these are the key points you've got to lock in.
Here's the whole story in a nutshell. First, this specific recurrence is the model for an algorithm that does a linear amount of work and then makes one recursive call on a problem that's half the size. Second, that structure always creates a geometric series of work. Third, because of how that series works, the cost is front-loaded. That first step at the root does the most work. And finally, all of this simplifies down to a nice, clean, linear time complexity, O of n.
And I'll leave you with a little something to chew on. We just solved this for when the extra work was n. But what if it was just a constant amount of work at each step, something like +1? That would be the recurrence for an algorithm like, say, binary search. How would that change the tree? How would it change the sum? And what would be the final big O? Think about that one, because if you can solve that, you're in really good shape with recurrence relations.